Right. It's a pleasure for me to introduce to you Joe Leibo. Joe has a PhD from MIT as a computational neuroscientist and machine learning, what you said, expert. But then already doing his PhD, he joined DeepMind. So he was actually one, if I understood correctly, one of the first researchers at DeepMind, even before DeepMind was then later acquired by Google. And now he's a senior research scientist at DeepMind. Yes, super happy to have you here with us. Actually, your work has been quite influential from my way of thinking, and I want to just pick out one specific work, which is I will shorten the title of it, like the Manifesto for Multi-Agent Intelligence Research. And I mean, there has been a lot of work kind of unifying biological evolution and cultural evolution, like, for instance, Lala, Soli, Server, and others, but you kind of brought into the same kind of framework now with formal learning. And I think that's quite interesting to kind of think of all these phenomena as essentially systems of adaptive learning units. And this type of learning can be genes, can be cultural amplifiers, can be weights in another. And so the overarching idea is you have this interactive learning systems which because of that adaptiveness, drive the system out of equilibrium. Then they might produce new challenges which these adaptive units have to adapt to, and they might promote innovation. And this is kind of like an iterative process, at least to like to an emergent curriculum, like which you turn that out of with. Yeah, if you look at DeepMind in the field of reinforcement learning, specifically multi-agent reinforcement learning, has been impressive, really. And I'm sure we'll talk about that and all the implication. But what I just said, I found like really specific that you seem to always ground your research also in the literature of social science, kind of really work on this interaction of social science and AI research. And I really think there's a lot of potential, which, I mean, we all know that there has been this mutual benefit from the neuroscience and AI research, and like kind of innovation went back and forth. And yeah, as we just said, like human intelligence is always like it's bounded in the social environment, and there's like no reason to not think that the same kind of mutual beneficial interaction cannot happen also between social science and AI research. So I hope that this talk will kind of inspire both fields, like both the people who are interested in AI and also people interested in social science. And yeah, the floor is yours. I'm excited to about the talk.
Thank you for that very, very kind introduction. Do I need to do something to start this with the hybrid thing? I guess it's just working, I think. Great. Cool. Really excited to be here and talk to everyone. And so, like Levin said, I've been interested in this kind of viewpoint where there's a space between taking inspiration from social science into AI and back and forth, just like exists already in neuroscience. It has existed for a long time with a virtuous circle of insights from neuroscience to AI and back from AI to neuroscience. I think maybe because I am a neuroscientist by training and at heart in some sense, I kind of imported one to this kind of new space where I'm interested in more social science connections. But I'm also not actually a social scientist, I think is important. So I have no respect for disciplinary boundaries within the social sciences. So I'll pull from anthropology on the one side or economics on the other side and kind of mix things together in ways that probably annoy any actual social scientists. So I'll apologize for that at the start. Okay, so I'm going to talk about multi-agent artificial general intelligence, MAGI. I'll start with some kind of this terminology kind of slide. So we talk about AI a lot, we talk about AGI, and I talk about MAGI. I don't know if we talk about it. I'm not sure who talks about MAGI except me, but I do. So I often talk about, well, I'll also say narrow AGI most of the time, to when I mean like specific applications, like anything that does any particular thing is some kind of narrow AI. AGI is this term a lot of people use for something that usually means some single AI that can do many, many different things. It often is connected with the idea of a human level AI, though it sort of is more general than that. It could mean like it can do any task, including tasks that people are bad at. Yeah, also you could also imagine having an AGI that is worse than human level. It's just more about the generality. And also you could have one that is not human-like in any way. That would also be possible. So it's really a different dimension. But the one I want to talk about is this MAGI dimension, which is multi-agent AGI. So that would mean something that's kind of a multi-agent system rather than a single agent, but has otherwise properties like AGI, where it's able to do lots of tasks. But instead of do lots of tasks, it's more like be in lots of social situations and act appropriately, something like that. And so I think it would be good to try to build a MAGI, maybe better than trying to build an AGI. And I think if we can do that, there may be two reasons. One is that it might be more human-like, because I think humans might be better captured as a multi-agent intelligence than as a single-agent intelligence. And it also might be better, more human-compatible, or at least thinking about such a system might make you more likely to make better choices in what you deploy and how you deploy things. And also, if you have a lot of different actors who are trying to build an AGI at the same time, then you're going to end up with a MAGI regardless. And so we should think about it. All right, so through this talk, I kind of contrast a bit with a single agent perspective. You can see that as the narrow AGI view. Sometimes I'll call it the solipsistic AGI view. But I also want to contrast with a particular variant of that, which is the human-like version. So if you want to build an AGI that's human-like, and many people do, one way that tends to go is you'll talk about reverse engineering. A lot of people will say this is like the banner that their research falls under. A lot of like cognitive science-inspired AI work does. And so usually the reverse engineering perspective works is you'll say, okay, I want to build this artificial agent that is like human in various ways. So I'll try to say, okay, well, humans have certain properties of their perception systems, their attention system, their memory, planning. All I need to do is get all those parts into the agent as like different modules. And that's a kind of and those are like the classic cognitive abilities. But I think those are not really the things that are impressive about humans, as I was saying. I want to build a MAGI, a MAGI, a multi-agent intelligence. So I think the things that are really impressive about human intelligence are more like how we relate to each other, how we are good at cooperating, we are good at learning from each other, we're good at coming up with conventions, we can speak language, and we can do all these things that feel more like multi-agent properties. The things that are impressive about humanity are really our achievements as a group, more so than our achievements of individual intelligence, I think. And so I want to set out a research program that maintains the idea of doing reverse engineering in order to get something human-like, but it's reverse engineering human intelligence now to build an MAGI rather than an AGI. And the question is, what's the analog now? Like, what's the analog of this picture? Are there parts to that in the same way that there were parts of the single agent perspective? And this is just another slide where I used to argue that humans really are like ultrasocial in some sense. This is a paper from Esther Herman and like Tomasello and many others, where it's probably familiar to people in this audience maybe, where this is just a paper that was arguing that humans are especially good at learning from one another, and that's what's distinguishing us from other animals, which are maybe similarly intelligent in our individual abilities. So in that paper, they're comparing chimpanzees and orangutans and human children and kind of like IQ test type things that they designed for this purpose. You can see them written there, but it's probably too small to read. They're things like they were divided into two different parts. There were like physical tests and social tests. The physical tests were things like finding a reward, tracking a reward after invisible displacement, tracking a reward after rotation manipulation, discriminating quantity, and some causal understanding of a noise produced by hidden rewards. It says using a stick to retrieve a reward out of reach is kind of physical IQ test type things. And then the social ones were things like solving a simple but not obvious problem by observing a demonstrated solution, producing communicative gestures, following an actor's gaze, these kind of things. And they find that the humans, chimpanzees, and orangutans are all basically at the same level on the physical ones, but the humans are way better than the chimpanzees and orangutans on the social ones. And why did they have to use 3-year-olds even though they use adult chimpanzees and orangutans? And that's because if you used adult humans, they would of course just be at ceiling on every single one of these questions, right? So the idea is that humans and human intelligence does more day to day than chimpanzees or orangutans. I'm also happy to take questions as I talk, right?
Regarding, like, for example, when you mentioned theory of mind, is it accurate that chimpanzees follow also chimpanzees?
Oh, I don't know. So is it that chimpanzee theory of mind question? Yeah, I don't know. People have studied that. I think it's controversial whether they do or not. I'm not actually sure. I think that it is known, though. I just don't know. Regardless of whether it is or not, there's lots of other social abilities, and if you just kind of like a cut of them here, you find that averaging across the children are better. But why would adults be at ceiling, right? And it's because the idea is that there's this initial difference. So the children are just they're more tolerant of each other, they're more kind of oriented toward each other, more able to learn from each other. And that's the initial difference. And then by the time they're adults, they can do all of these things and much, much more. That's where I was really going with this. So the point is that we're in a kind of a cultural intelligence, cooperative intelligence niche that the chimpanzees and orangutans just aren't. And that's kind of critical to how we go about our lives and survive. So I find that cool. What's actually different though, right? Or what's actually, I'm not really going to be talking about comparing to chimpanzees and orangutans here. I'm going to be talking about building something new, right? So what are the kind of social cognitive capacities, representations, and motivations that underlie our ability to cooperate and learn from each other and everything else? And so, because this paper didn't tell us any of that in particular, right? It could be that theory of mind is underneath or not or whatever. And so, these are lists of things on this slide, right? Initially, this slide was meant to be kind of the an analog to this one, right? We're saying what's the and there's a single agent perspective where you have a bunch of classic cognitive abilities, perception, attention, memory. Those are like the parts of the single agent mind you might want to put together. But what are the parts of the multi-agent system that you can think about in a similar way? And so initially I wanted this slide to say something like, what are the social cognitive capacities? But then I thought more about it and I was like, well, it seems like things that might matter for cooperation and humans' ability to learn from each other are not all really anything like cognitive abilities. Some of them are more like representations and some of them might be more like motivations. If it's representations, it could be like we were very good at representing social relationship graph, or representing people by parsing them into social identities that then predict what they might do in different situations. Maybe we have good memory for individuals. Those are kind of representational things that might be different. There also could be things that feel more like motivations, like we have certain emotions that it might have particular like social effects, like fear and envy, shame, and ability to provide social rewards. And then also we do have plenty of capacities that might be unique about us, like our ability to understand other minds or communicate better, and something important there. Maybe something about empathy is something different, or some capacity for imitation. And also we think all whatever these initial kind of capacities are, they are probably underpinning all kinds of complicated social behaviors, a bunch of which are listed on the slide here. And which are themselves scaffolding further learning, right? We have institutions of education, which we use to learn patterns of thinking, which extend our abilities in all kinds of new directions that chimpanzees don't have. And neither do reinforcement learning agents most of the time, unless we build them that way. So, okay, so we can ask things like, what were the challenges in our evolutionary past that drove the evolution of these social cognitive capacities, representations, and motivations? That's a mouthful name, SCCRMS, that's these things. So what drove these? And why does this matter for AI? So one approach to building a general artificial intelligence, or a multi-agent general artificial intelligence, would be simulating these things and using them as some kind of training ground where generic reinforcement learning agents could then discover, these would be driven there as well. But this doesn't mean a research program that's just like simulate everything on Earth and hope for the best. I do think that there are kind of principles here, and there's not necessarily a gigantic number of them. It could be a relatively small number that is actually ascertainable, and we can study that with this kind of approach. But to do that, we have to embrace kind of a diversity of challenges in the challenge space. So we should be aware of dangers of abstracting things along dimensions that aren't ultimately the right ones. So we need to have a research program that allows us to try different ways of abstracting problems. So one thing in particular that I always contrast with is there's of course a gigantic, years and years of work built up over time on iterated prisoner's dilemma, which is one particular abstraction of a cooperation challenge, but there could be much more to cooperation than that. And abstracting everything always as prisoner's dilemma, it's surely missing something. So this is a good point to talk about melting pot. We created this suite of different environments, which are all kinds of different social challenges, trying to get all kinds of different incentive structures. So everything from zero-sum games to more kind of cooperative, fully cooperative things with a large space of mixed motivation, social dilemmas, and things like that in between. And I'll say more about this as I go on, basically. But just know that all of the different kind of environments I talk about throughout this talk, they're mostly all in this repository, which is open and anyone can use and also can contribute to. There's much more I could say about it, but I'll probably save that for the end. But it's a platform to study the kinds of things I'm talking about. And in particular, to do it in a way that's not necessarily just prisoner's dilemma, but to have more complex kind of instantiations of problems. I got this perspective from reading Elinor Ostrom's work. She was probably by far the most influential person I've read for me. I've started reading her work maybe more than 5 years ago now. So for anyone, I don't know, actually, I always like to ask. So in this audience, who has heard of her before? Okay, cool. We got some in this audience. I sometimes get I either get like everyone has heard of her or 0 people have heard of her. It's nice to see a mixed audience. So for anyone who doesn't know, she was the first woman to win the Nobel Prize in Economics, which she won in 2009, and she passed away a few years after that. So I never actually met her, and I learned about her work after that. But she is famous for she's expert on tragedy of the commons kind of scenarios and institutions that it's about how do people in the real world solve actual like resource management problems by creating institutions. That's really her topic. And one way to quickly talk about it is so there's a everything with prisoner's dilemma view of the world, which would say that all resource management problems are impossible because prisoner's dilemma is a game where there's only one equilibrium and it's a defect outcome. So anytime you have a common pool resource, like something where there's a prisoner's dilemma, reasonable to model it as a prisoner's dilemma. Those are intractable problems. There's nothing can be done. All you can do is like radically change the incentives, either by paying people to do something different or punishing them for doing something else and completely changing the game. And Elinor Ostrom came along and said, well, but like, what about all these places in real life where there's here there's a fishery that's being managed successfully, and here there's a common pasture that's been held for hundreds of years, and here's an irrigation system that hasn't collapsed, and also she talks about places that have failed, right? But sometimes it does work, and so the quote that people always use from her is if you have in response to the theory that says it should be impossible, she was saying, well, if a resource arrangement works in real life, surely it must also work in theory. And it was motivating for her, whole research program and why she won the Nobel Prize. But the thing that I take away from it, really, that motivated me was the fact that she really embraces the differences between different resources. Rather than seeing everything as prisoner's dilemma, she'll say, okay, how is an irrigation system different from a forest, different from a pasture? And how do they create different kinds of incentives and make it so different kinds of institutional interventions will work or not work? And so that became really the kind of central motivation for a lot of the environment design that we've done. Like that's why melting pot, our suite here, is a large number of different environments with different characteristics. So we can see like, well, what works for cooperation here might not work there, and try to understand something from the common patterns across all of it. Solutions now, going back to this picture of like, what are we reverse engineering? Like we're reverse engineering the multi-agent system now. A lot of these things end up being, you could see them as inductive biases or cognitive modules or something like that. But they don't have to have those kind of like nature versus nurture type interpretations. You could also see them as like kind of cultural elements that are there before the finger modeling. But also, what we found increasingly as we started doing this is that a lot of interesting problems get solved without doing anything in particular. So I'll now, for the rest of the talk, kind of go into a bunch of different examples, and I think I'll go a ways in before I have to get to anything that requires us to do anything beyond run generic tabula rasa reinforcement learning agents. I'll keep going. Okay, so back to the view on how different problems are really different from each other. This is kind of one cut above how you can think about that. So people may have seen this picture before. It's kind of a common like intro economics thing you can do. And it's about classifying goods or classifying resources. And there's two dimensions here. There's a subtractability dimension, which is about if you deplete the resource, is it actually gone? If you use it does it get depleted? And then there's an excludability dimension, which is about access control. I'll maybe quickly talk about what are the different parts of this picture here, because then it'll be useful for framing the rest. So so let's first look in the upper left there. So these are goods that are subtractable and excludable. This is where private goods land. So like food, clothing, car, things that you can kind of own yourself. Others can't access them once you own them. And also when you use them, they get depleted. Like if you eat some food, then that food is gone. You can go to the, move along the excludability dimension from there to the upper right, and now you have common pool resources. So these are non-excludable and still subtractable. So this is like all the fish in a fishery, or the timber in a forest, or groundwater, or other kind of common space in a common pasture, or like public parking spaces or something like that, where it gets depleted if you use it, but also there is open access to anyone. This is a place where you typically use the word tragedy of the commons for the bad outcomes that can happen. Also, you can go down from there to the lower right, and this is so now these are things that are non-subtractable and non-excludable. So this is like, these are called public goods, and these is like, clean air or national defense for everyone kind of stuff. These are things that are not depleted when you enjoy them. Like I can enjoy the clean air just as you can enjoy the clean air. It doesn't matter how many people do that. Also there's no access control issues. Like it's kind of for everyone and not depleted. And here the issues, there are also social dilemmas, but the issues are slightly different from in the common pool case. Here the issue is not overconsumption, but actually it's difficult to invest in providing them. Like it's difficult to get anyone to invest in cleaning the air because maybe someone else will do it. There's a free rider issue. So it's a big problem. So these are the places where there are social dilemmas, classically. Another point to make here, which is another really Ostrom-like point, is that these, in the kind of economics 101 version of the world, you would treat all these as like very, like perfect properties that are like you either have these properties or you don't. But you can really also think of these things as non-absolutes. And so, particularly the excludability dimension, it's interesting to think about like, well, maybe it's sort of excludable. Like you could do it like with some effort or something like that. And so I'm going to talk a bit about that for the rest of the talk, but I'm going to start in one corner. I'm going to kind of move around, making these things kind of, relaxing various parts of this. Okay, so I think I'm going to start with private goods. Okay, so private goods. I said in the beginning that there was going to be lots of cases where we don't need any special social cognitive capacities, representations, and motivations. This is going to be one of them. So, all right, this is what it looks like. So we came up with this environment, and what we ended up studying was the emergence of barter. So this is meant to be a private good here. So I think this isn't, I can start talking about this in different places. This is interesting in the place that, according to this picture, and maybe could have started somewhere else where it would be like, it would feel more like a hunter-gatherer scenario. This is going to feel very different as a starting point because it's already assuming some kind of private property concept. So this is probably not a good place to start if you're thinking about evolution, but is maybe a okay place to start if you're thinking about kind of matching this economics diagram. And it is typically the way you would talk about things in an economics class. Like you would start with private goods because they're like the simplest from that perspective. So let's start there for now. Okay, so here's the game. So in this world, there are two resources, apples and bananas. Agents can harvest fruit from trees by walking over to them and standing on them, apparently. And they have an action to consume the fruit. So they have an inventory, which they can see. It's not visualized here, but they can see their inventory. And they can choose to eat things at any time that are in their inventory. They can also make offers to trade with each other. They can trade with agents that are nearby them. And the actions that they have a meaning like, I'll give you 1 apple to get 1 banana. Or I'll give you 3 bananas to get 2 apples. And the trades happen whenever agents make inverse offers and are standing close to each other. Okay. And then the learning is tabula rasa multi-agent reinforcement learning. I say tabula rasa because it's just a generic neural network that has no particular inductive bias related to this task. And it's and by multi-agent reinforcement learning, I mean it basically works regardless of what algorithm you run. We did the initial work with VMPO, but I've replicated it now with A3C, and it doesn't matter. I'm sure it would work with PPO. This kind of thing is just kind of robust. It's more about the interactions in this environment makes things get learned. The particular algorithm doesn't matter. Okay, so this is what happens. So trade emerges, and as you might expect, and it's rewarding. So this is like the collective reward, like the sum of everyone's rewards. Of course, it's much higher if you allow them to trade than if you turn off the trade mechanism. Oh right, I forgot. There's a critical detail that should be on this slide, but it is not. So there's a reason for them to trade, which is that half of the agents are good at harvesting apples, but they want bananas. And the other half are good at harvesting bananas, but they want apples. And by good at, I mean the probability that they will be able to harvest it for every step that they try. So if you watch the video, sometimes you see that they'll stand on a particular tree for a long time. That's because they're trying to harvest it, but they're not good at it. But if they kind of quickly, stop just quickly over the tree and keep moving, then that means that they're good at harvesting it. So the best thing to do for everyone to get a high reward is for them to use their comparative advantage, like harvest the thing you're good at and trade it for the thing you really want. And if everyone does that, that's fine. But also think about the problem here. It's got interesting multi-agent interactions because you can't just unilaterally do that. If you start doing that while others are doing something else, then it won't be helpful for you. You'll just end up with lower reward because you're harvesting the thing that you don't actually want. Also, there's multiple equilibria here, right? There's a bad outcome, the autarkic outcome, where everyone just harvests the thing that they really want, ignoring the fact that they're good at harvesting the other thing and not trading. But we find that they do discover trade, and they do end up finding the better outcome here. You can see that there's kind of price exploration over the course of learning here. In this picture on the right, in this particular run, it looks like it was kind of a 3 apples for 3 bananas was the trade that won in the end. But you can see they kind of explored different ones throughout. This kind of is a cool setup. You can do kind of economic style perturbations, and you can plot supply and demand curves and things by changing proportions of trees. You can create supply and demand shocks and rerun the experiment in different conditions and kind of draw out these things. The predictions all really hold. This does seem like a perfect competition setting in the way economists think about it in the end. And you get kind of these intersecting supply and demand curves as they would expect. So that was kind of cool. The most interesting thing that happens, though, is this merchant-like behavior that emerges in this setting. So this is a different map now with 3 sections. There's a mostly apples on the left and mostly bananas on the right. So in the left, if you just have your whole version of the experiment there, it'll be like a setting where apples are cheap and bananas are expensive, like in the supply and demand curve. Because there's mostly apples here, so apples should be cheap. And then on the right, you get the symmetric case, so mostly bananas, so bananas end up cheap and apples become expensive there. In the middle part, there is an equal mix of them, but it's like more sparse. And there's walls between. The agents can trade over the walls, but they can't walk through the walls. So whichever section you're starting in, you're stuck there forever, but you can trade with others across. And so what we found in this case was that this behavior emerges where the agents in the middle, they stop harvesting anything themselves, and they just end up with this kind of transporting and selling goods. They'll like buy apples where they're cheap and sell them where they're expensive, and vice versa, and kind of circle around and do that. And they end up getting higher rewards than any of the other agents for doing this. So this was an interesting outcome here. And a cool thing about this is it's really you needed a kind of stage-wise sequence of events to emerge for this to work. Right? It has to first be that agents figure out that they can trade, and they figure out what the right price should be in the left and the right, and those equilibria emerge. And then only after that has happened do the agents in the middle, then suddenly it makes sense for them to start switching from their own emergent equilibrium to this other behavior where they can trade with each other. So it's really a sequence of things that emerge here, and it kind of has to be in that order. I think that's a really interesting kind of pattern that we find in these kind of experiments, where you can develop complexity, but there's sort of a path dependence to it, which is neat. It's also an example of an autocurriculum, if anyone is interested in that. Okay, so back to this picture of goods here. So that was the private good picture. Let's talk more about the other side here, so about commons dilemmas. So, and then I'm going to kind of move between them a little bit. All right, so in this environment, which we called commons harvest, so agents move around in the world, as always, and they get rewarded for collecting apples. Here, they just collect the apples immediately when they step on them. And like in all of our games, they have a partial viewing window. They did in the previous one as well. And the apple growth rule is now density dependent. This is where the important rules come in. So this is what's going to make it a common pool resource. So it's going to make it kind of a sustainability type challenge. So here, the apples will grow more quickly if they're adjacent to other apples. So, and the probability of growth will drop all the way to 0 if there are no adjacent apples. So if you remove all the apples in a patch, then none will ever grow back in that patch. So you have a kind of trade-off between like eat very quickly, everything close around you, but then nothing will grow back, versus like leave one there and go do something else and then come back and they might have grown back by the time you come back. So it's kind of sort of short-term, long-term, intertemporal sustainability challenge. We call these intertemporal social dilemmas as well. Another feature of this game, which we have in many of our games, is that we allow agents to do punishment, dyadic punishment, where they have like a zapping timeout beam that if they zap another agent with, then that agent gets removed from the game for a while. If you're removed from the game, then you can't get any reward, so it's punishment. And they may not use that, right? Because you don't get any reward necessarily for doing that, but they may use it, may not. It lets us study sanctioning, and it lets it has a bunch of applications, and that's allowed here as well. Okay, so in this game, I'll show you a couple of versions. So if you make it a single player game like this, it's completely easy. So any reinforcement learning algorithm at all, again, doesn't matter, we'll learn something like this. This is basically the optimal thing to do, is to run back and forth between those two patches, never deplete either of them, and you can just kind of keep going forever this way. It's pretty much optimal. What we find is at the beginning of training, it does deplete them, right? Well, the beginning is random, it does nothing, it does something okay, but it just bounces around and eats them. But as it starts to learn, it'll start to deplete them, but then it'll get feedback as it keeps repeating episode after episode. They're like, oh, every time I deplete them, then I end up with lower reward, so I don't do that again. And it quickly figures out that it should just do this. But as soon as you make it a multi-agent situation, the situation is very different. And this video, I always have to show multiple times because if you blink, you'll miss it. It's so this is what happens in a multi-agent system. So they just immediately eat everything as fast as they possibly can, and that's really the way that the way the gradients are going, right? And you can train this for as long as you want. They'll never figure out to get away from this, right? Played a few times, it's all gone. And so this is only very early in the video, right? They get 0 reward for the whole rest of the episode, right? Keep playing it. Yeah. So why does this happen? And why is it so different from the single agent case? In the single agent case, they actually get feedback from the fact that if you don't deplete the patch, then you get a higher reward versus if you do. But in this case, if you explore, okay, maybe I won't take that last apple, well, then someone else will probably take it, and you don't get any feedback from that being the right thing to do. So there's no way to credit assign through this catastrophe that happens over everyone's actions.
But in this case, also, like, aren't there like less apples to make the
It doesn't matter. You can do you can make it much bigger. It's yeah. So the pressure on them is to eat as fast as they possibly can, which is because it's a race before others eat is the issue. And we've done this in like.
Sometimes they could just all die and then.
Yeah.
You know.
Yeah, well, evolution would always be more complicated, and the complications would offer the way out, as I'm going to show other versions as well. Because in the real world, it's never as simple as just this, like a big field where there's the only thing that can happen is this one thing, right? In the real world, the complications are part of the way out, right? Also true in Elinor Ostrom's examples. It's always more complicated than a prisoner's dilemma. That example is a bit too stark and a bit too much like that. Yeah, so you can also, so I previously showed you a private good, the barter example, and now I showed you a perfect common pool resource, right? But we can kind of play around with the space in between. And in particular, because this is a reinforcement learning setting, we can show examples where learning can manipulate how excludable the situation is. So here's one case like that. So in this case, exclusion ends up emerging from learning. So remember I mentioned there was this timeout beam that they have. What they can learn to do is kind of defend these choke points. And so one agent will be in there and will kind of defend the entrance and prevent others from entering. And then once they do that, they are able to be sustainable again, right? Is in the multi-agent case, because the agents know that once they're inside, they're likely to be able to stay there for a pretty long period of time. They can kind of defend it. And once they're there, they do get the feedback from like, oh, I shouldn't deplete it all, because across many episodes, they actually can learn that leaving some apples there is good because they will kind of monopolize the future flow of resources from that. So this is a case where you get sustainability from a kind of a privatization type outcome, but like it's different from in economics, you would usually say, like, let's just impose privatization and compare. Right. But here it's like the agents just learned on their own this kind of territorial strategy or something like that. So it's an interesting kind of way to solve the sustainability challenge and resolve the social dilemma. But of course, it's also it has other problems, right? Like you get huge inequality as an outcome for this. This is like inequality. This is like reward distribution as a function of different maps and different map structures and stuff. So it's not this isn't a good solution from like an overall like our perspective on the problem, but it's interesting that this is one way to resolve a social dilemma that would otherwise be there. And we might find that there's lots of if we really think about our own societies, there's lots of like kind of outcomes of other previous resolutions to different social dilemmas that create other social effects downstream that then might create new social dilemmas, and I think that really is a separate auto curriculum trying to resolve like new social problems that emerge from solutions to old ones. Okay, so everything I've told you so far hasn't required any work whatsoever on the reinforcement learning agent. It has been entirely off-the-shelf reinforcement learning agents, just like you put several of them in, you give them each their own individual reward, individual neural network, and just hit run. Nothing special at all. But there are plenty of problems also that do end up needing something. So I'll show you some. Right. So okay, so here's one that's going to be like that. So this one's called cleanup. This is more like a public goods problem, or quasi-public good scenario. So here, the way this game works is agents walk around in a 2D world. They get rewarded for eating apples, and as always, they have a partial viewing window around what they are. There's also, now the important rules, there's a river that is feeding kind of an orchard of apples. And if the river is filled with pollution, the apples don't grow. Agents can clean the river, and then that makes apples grow anywhere in the orchard, though. It's not like localized. But the orchard is displaced from the river. So you have a trade-off. You can go to the river and contribute to the public good by cleaning the pollution, and that will kind of create apples everywhere. It's not a perfect kind of pure situation, because it's not like you get reward directly for contributing. It's still kind of like, if you contribute, the agents that are standing there in the orchard already are likely to get more apples than you are. So there's some kind of temporality to these things. I'll show you what these looks like. So I forget which video is which here, so let me just see here. So this is, okay, so this is what a good solution would look like, where, or just, this is just showing you kind of the dynamics of the environment, basically. Those two agents are running around cleaning pollution, and then the others are eating. This is not what any reinforcement learning algorithm would ever come up with, because if you look at this, the two agents that are doing the cleaning are getting 0 reward. They never eat an apple at all. This we had to make by giving them some special reward to just to make this video to show here, because nothing will ever come out looking like this. But I wanted to show something that shows you like what can happen in this environment. Yeah, that's what it would look like. The reason that this doesn't happen is you can see this is a video from early on in training when they're all pretty random, kind of exploring a bit. You see this yellow one has started to learn a little bit that it should try to clean. But what just happened there was that it cleaned a little bit, and that caused a few apples to appear. But then that other agent ate the apple before it could. So it didn't get any reinforcement for that action. So it's reinforcement learning. How can it ever get a gradient from that? And now it's trying again. Okay, it's doing some cleaning, but it's it's not terribly efficient at it. So no apples appeared, right? But to get more efficient at it, it would need to get more reinforcement for that. So it's not getting enough reinforcement from actually. From cleaning for this to work. And the problem is that the better it gets at cleaning, the more reinforcement the other agents are getting for eating. So they'll get more efficient at kind of searching that space on the side for apples to appear. And so the gradients point away from cleaning, because it's even less likely to eat anything. All the gradients point towards spend all your time in the orchard and none of your time cleaning. So it's a very difficult problem from the perspective of the following the reinforcement learning gradients. You definitely need to do something different to solve it. So now we come back to thinking about these kind of inductive biases, things like that. And we've studied this problem for a number of years now. We have found a whole bunch of different things that work. These are all different papers that have explored different ways of solving it, and some of them not ours as well. I could talk about any of these really, and I'll just kind of quickly mention them basically. So one is inequity aversion. So if you put in some kind of models of where agents are penalized, internally penalized for doing better or worse than others, that's one way to get to an outcome here. You can also have this kind of personality psychology model, like this social value orientation thing, which is like there's some people are altruistic, some agents could be. There's also an evolutionary group selection model, which is really the results are in line with what you'd expect from evolutionary theory, where if you do anything with an individual fitness, then you never learn altruism or evolve altruism. But if you do something with group selection, where you're kind of selecting groups at a time, then you can evolve altruistic policies, which works here too. Also kind of a reciprocity model, which I will talk about in a second, and then some work from a group at MIT, from Dylan Hatfield and Else group. He was showing if you give agents kind of a ability to make contracts with each other, like binding contracts, or I think reward transfer contracts in a particular kind of language, then that's another way to solve it. So there's lots of ways to solve it. And I'll talk for a minute about the reciprocity one, and then I'll talk about a reputation one, I think, then I'll be done. So the reciprocity one was of course inspired by Axelrod's work on tit for tat, and he had these principles like agents should be nice. He was thinking about iterated prisoners dilemma, so saying you should cooperate first is one principle. You should be clear, have like a legible strategy that others can adapt to, and you should reciprocate antisocial behavior because you have to punish wrongdoing, but you also have to forgive over time. And he says those principles imply you should run tit for tat. But it's unclear what these would mean in a more complicated environment like this. Like tit for tat makes sense in iterated prisoner's dilemma, but what does that mean here? So here's our version of it, right? Here's the problem, right? So the problem is that it's not clear what exactly is prosocial or antisocial behavior in a complicated world like this. All these behaviors consist of like long sequences of actions, so there's no single thing. Also, you might want to respond slightly differently for what your opponent did. There's also time delays, and there could be lots of players. So lots of obstacles. In ours, the way we did it was we divided the agents into two groups. We said half of them are innovators and some number of them are imitators. and the imitators will try to copy the valence of what the innovators are doing, like how pro-social was it what they did. The way I think this worked, let's see. Oh yeah, what's hard about it first, actually, before I talk about the solution? Yeah, so why doesn't generic reinforcement learning learn this actually? Before we say anything about how our solution worked. The reason generic reinforcement learning doesn't work is that you would have to why is it that you can't learn to teach with these methods? The reason you can't learn to teach is that you would have to be doing credit assignment through someone else's learning. But the learning of the other is too slow, takes too long, or at least it's on the same time scale as your own learning. So you can't really, there's like a chicken and the egg problem. Like they would have had to already do it consistently before you could get a reward for having changed their behavior, right? So it's a chicken and egg type problem. And so you have to do something else to break that. And this is the way we did it. So we divided them up into imitators and innovators. The imitators have a special intrinsic reward, which is like an extra term in the reward function you add in, which looked like this, and it had this N of T thing here. So this was what we called the niceness network. They were kind of estimating how pro-social was the actions of the others and trying to match the pro-socialness level of what they did. So then it ends up being like tit for tat reciprocity, because if you do something that is nice, then they will respond with something that is nice. But if you do something that is mean, they'll respond with something that is mean. And if you are a naive agent learning in that environment with these imitators, then you'll learn to cooperate because they'll imitate back to you the cooperation. And so that is one way to solve this problem, as this shows. And it also works in the open field harvesting game as well, the common pool resource one. Okay, so I'll try to do this last one quickly. So these kind of problems were entirely in simulation, but we could ask how to kind of validate this line of work in real people as well. Now we can't manipulate like a sense of whether you want to do reciprocity, but there are some things we can manipulate in a human experiment. And in particular, what we could do is manipulate anonymity. Reputation should be another way to solve this. So that's what we did. So the idea was we would have humans play this game, and we would manipulate anonymity and try to show an effect. So, and then try to come up with a model that matches it really. So, what we find is that humans can resolve it in the identifiable case. If you let people play this game in two conditions, one where they're anonymous, where they're all the same color, they all look the same as each other, and one where they're identifiable, or they have like defined, you're the blue player, the green player, yellow player, whatever. They solve it in the identifiable case. They don't solve it in the anonymous case. So we had the effect in humans. And this is, what the thing looked like. And then we had a model that was trying to match this. So in this model, it's another kind of intrinsic motivation model where you add another term onto a reward function. But here, the term that you're adding is measuring the kind of it's a kind of a reputation proxy. It's assuming common knowledge of cleaning being good, but it's like how much did you clean basically, as seen by the others. And that is another way to do this, and you can kind of simulate the whole experiment with the two conditions, with the anonymous condition and the identifiable condition, and you can show very close results match between the humans and the agents. But you can also do more than so far. I haven't really said anything so different from what you could do in a public goods game or something like that, in a abstracted public goods game. But here you can do some more fine-grained kind of interesting things. Like you can look at how they solve it. That's really the strength of this kind of method, right? You can say, did they solve it in a way that was, there's different ways of going about it. Like, so in this environment, you could do it in a kind of a turn-taking way. You could do it in a more territorial way. Like the territorial way would be like, I'm responsible for this chunk of river, you're responsible for that chunk of river, and divide up the river. And people might have done it that way. Or they might do it in a turn-taking way, where it's just like, it's my turn, now I'm responsible for the whole river, and then next is your turn, you're responsible for the whole river, and you cycle around. And what we find is that humans solve it in the turn-taking way, not the territorial way, and also so do our agents. Well, I think, you can't even see which is which here. And also in a mediation analysis, you find that the effect of the manipulation, the identifiability and anonymity manipulation, is mediated by how much turn-taking they're doing, the effect on collective roof trend. So that's cool. So I see that the time is running short, so I'll try to end around here. So I'm arguing that we can model these kinds of motivations that give rise to the emergence of social cognitive capacities, representations, and motivations, and that an MAGI, a MAGI, as a kind of objective of what we want to build, may ultimately be a more human-like type of thing, and possibly make us think about more of the issues that would be needed to make it more human compatible in the end for thinking about sustainability and cooperation and things like that. And I'll end on melting pot again. So we have this suite of environments that you can run any of the things I talked about, or many, many others. There's more than 50 different environments in there and 250 different kind of test scenarios and stuff. It's a whole kind of generalization framework. I can say much more, but you can also go to the website and check it out. And it's kind of, it has ambitions for comprehensiveness in a sense of like, we would like it to ultimately cover all social phenomena that people are in the community are interested in. So, so add to it, and it will expand. And I'll take questions now.